Hello everyone, myself Ejaz Ahmed Deliwala. I am a PhD research scholar at the Department of Aerospace Engineering, IIT Bombay. I am a TA for today's lab AE314 AE727. Today we are going to conduct an experiment, Flexure Test. What is Flexure Test? Flexure tests are generally used to determine the flexural modulus or flexural strength of a material. So why do we require a flexure test? So the most common purpose of a flexure test is to measure the flexural strength and modulus and use these values to evaluate the sample's material's ability to withstand flexure or bending forces. So whenever a specimen is placed under flexural loading or transverse loading, there are three fundamental stresses which are present in the specimen. So these are tensile, compressive and shear. So the flexural properties of a specimen are the result of the combined effect of all the three. What are the different types of flexural tests? So there are basically two types, 3-point bending test and 4-point bending test. So this is the figure which you can see for the different configurations. So in a 3-point bending test, the name comes from there are two supports and 1 point of load. So that is why the name comes 3-point bending. And similarly for a 4-point bending test. So there are two supports and two loads, 2 points of applications. So as we all know how to determine the shear force and bending moment diagram of a simply supported beam with a concentrated load at the center. So this is the shear force diagram, and what we see is that at the point of application of load, the shear force changes sign and the bending moment is maximum at the center. So our material will fail along the center. And in the case of a 4-point bending test, what we see is that near the application of load, there is no shear force and the bending moment becomes constant over these 2 points. So for a flexural test, it is very important that the bending moment is constant, and this will give a more accurate result as compared to a 3-point bending test. A flexure test produces tensile stress in the convex side of the specimen and compression stress in the concave side. So this creates an area of shear stress along the midline. And we want to ensure that in our 3-point bending test, the primary failure comes from tensile or compression, and therefore the shear stress needs to be minimized. So this is done by controlling the span to depth ratio. So the span here is nothing but the length between the supports. So the length of this outer span divided by the depth of the specimen should be, for metals it is around 16, and some other materials require values greater than 16 so that the shear stress is low enough. So for our test today, we are going to use a 3-point bending test setup. So today we are going to do a flexure test, and this is the UTM machine which you have already seen in the tensile test experiment. So the setup here is of a 3-point bending setup. So the lower part is the support base, which is used for supporting the specimen, and we have an upper nose which is a loading nose. So this loading nose will be exactly at the center of the specimen. So the first step is to measure the dimensions of the specimen. So we will be measuring the thickness, the width and the total length of the specimen. So the next step is to align the specimen in such a way that it is exactly under the loading nose. We can see the markings in the lower base. So it is set according to the support span. The support span for this material is around 162 mm. So we get an S/D ratio of 54. Now the test starts, and when the transverse load is applied, the top surface goes in compression and the bottom surface goes in tension. So we can see the live display of load versus extension for the 3-point bending test, and as it reaches the peak value we can see the load drop where the specimen fails. So this is the final specimen after the flexure test. So we can see because of 3-point bending, and we can see the broken specimen, broken line over here. So the observations should be noted in a tabular format, and we will be providing you the specimen width, thickness and length. So the length over here is the support span which we will be providing you. And the calculations, what you have to do is you have to calculate the flexural strength of the specimen given by the formula below and the modulus of elasticity. So here P is the load, L is the length, B is the width, D is the thickness, and M is the slope of the curve. So the assignment for the flexure test is that you have to plot the graphs between the load and deflection in order to obtain the modulus of elasticity and the slope of the graph to obtain the flexural strength. And then we will be providing you 5 to 6 samples of GFRP so that you can calculate the mean, variance, standard deviation of parameters, that is the flexural strength and modulus. And the exercises that are given in your lab manual. Thank you.